Okay, so this is where we're getting to some really algebraical stuff. So today's lesson is going to be solving linear systems by graphing, which we have done before using the Desmos calculator, which technically you can still use, but it's cheating. So I want you guys to get good at graphing by hand. So let's, essential question, how can you find the solution of a linear system by graphing? So some things to know about solutions of linear systems is that they have multiple options for solutions. So the first thing you can have is infinite solutions, which the book also refers to as consistent and dependent. And what it means is that every point on the line is a solution to the linear system. And some characteristics just by looking at the equations, if they're infinite, they're going to have the same slope and the same y-intercept. And then what it looks like is on a graph is two lines really right on top of each other. So if I zoom in, see how the red line's on top of the green line? That means it's infinite solutions because they happen to be the exact same line. No solution means that there's no solution to the linear system or the lines do not cross. And what the equations have in common is that they're going to have the same slope. So when I look at the graph, see how they have the same slope? They're both going up and over the same amount. But notice that they don't cross. If it looks like this, it means that it has no solution. And then finally, one solution, which is the one we're most familiar with, usually when we graph it has one solution, means that there is a solution and there's only one, and they cross at the exact same spot. And characteristics that the equations share is that they just have different slope and different y-intercept. Or they could have the same y-intercept, but they do have different slope. So notice here, I got a line with a negative slope, I got an undefined slope, and they cross right there, which is the solution. So we're going to jump into some examples. We're going to solve the system by graphing. And I know you guys are really comfortable with rearranging the equation and graphing it as y equals mx plus b. We can do that, but for me, I actually find it really easy to kind of go ahead and graph the intercepts. So that's what I'm going to do. So when I graph the intercepts, I'm really looking at the equation 2x plus y equals 6. And, oops, I'll put a letter there. And when I find the x-intercept, then I'm plugging in 0 for y. So then I get, let's just write it, x-intercept. I'm going to have 2x equals 6. So then I end up with x is equal to 3. That's my x-intercept. And then for the y-intercept, I'm plugging in 0 for x and solving for y. And so when I do that, I get y is equal to 6. So I have my x-intercept and my y-intercept for my first one. So I'm just going to go ahead and graph it. So my x-intercept is going to be at 3. My y-intercept's at 6. And then I'm just going to connect these with a line. So I could also have gone back and rearranged the equation, but because I find the x-intercept, like this is actually math you can do in your head, I just found it easier to go ahead and find the x-intercept and y-intercept and graph them. I'm going to do the same thing. And the reason why I'm choosing x-intercepts and y-intercepts is because notice how the equations in standard form. That makes it the perfect candidate for using the intercepts because, again, finding it's really just a one or two step equation. So we'll use, for the second equation, remember that it's negative x plus y equals 3. So for this one, I'm just going to use blue so you can see that's different. So then the x-intercept, when I'm plugging in 0 for y, so then I have negative x equals 3. Divide by negative 1, I get x is equal to negative 3. So in this one, my x-intercept is negative 3. And then when I find the y-intercept, I'm plugging in 0 for x. Sorry, that was very loud. 0 for x, and then I get y is equal to 3. So then when I graph this equation, I'm going to use blue. I'm going to have my x-intercept at negative 3, y-intercept at 3, draw my line. I'll make a straight line. There we go. And so then now the solution is where the lines cross. And so I'm going to mark that with a red. If I look at my graph, and then it looks like they cross right here, which is the point 1, 4. So I'm going to plug in 1, 4. I'm going to say 1, 4. And in order to check it, basically this needs to be a true statement for both equations. So to check it, I'm going to see if 2, when I plug in 1, 4, if it equals 6 for the first equation, and if it equals 3 for the second equation. So I'm going to 2 times 1 plus 4 equals 6. Well, then I get 2 plus 4. So 6 equals 6. So it works for the first equation. So then I have to check for the second equation. So then I'm going to have negative 2 plus 4 equals 3. I need to see if that works. Or sorry, negative 1. My bad. Negative 1, like, that's not going to work. Negative 1 plus 4 equals 3. And sure enough, I get 3 is equal to 3. So the second point, so it is a solution. It's a solution because it works for the first equation and it works for the second equation. So that's how I know my point is a solution. So the solution is the point 1, 4. So not too crazy, okay? Next thing, same thing. I'm actually going to do it 2 different ways. So this time I'm not going to find the x-intercept and the y-intercept. I'm just going to focus on finding, I'm going to graph the first equation because it's in y equals mx plus b, and then I'm going to use the intercepts for the second equation. So let's start by graphing the first equation. We'll do this one in green. Get lots of different colors on here today. So because it's negative 2x minus 2, I'm going to start at negative 2. And then remember, we're going up 2 over 1 using rise over run. Go ahead and draw my line. Oh, that's not. That is a rectangle. There we go. All right, so that's going to be my first line. And then the next line, I'm going to use the intercepts. So let's go ahead and calculate what those intercepts would be. I'm going to do, well, let's just write the equation. 3y plus 6x equals 18. If I find the x-intercept, then I'm checking to see if when y is 0. So I'm looking at the equation 6x equals 18. It means that x is going to equal 3, because remember, all I have to do is divide. So my x-intercept is 3. And then for the y-intercept, I'm going to plug in 0 for x, so then I get 3y equals 18. And then if I solve for y, I get y is equal to 6, because again, just dividing by 3. So I got my x-intercept and my y-intercept. So let's go ahead and graph those points. I'm going to graph a point at x is equal to 3. Going to graph a point at y is equal to 6. Going to connect these bad boys with a line. There we go. And look, they happen to cross right there. Look at that. So amazing. Right there. Oh, use the wrong color. There we go. So that is the point 2, 2. And for the sake of time and not making you want to watch a 30-minute video, I would want you to check to make sure that's a solution. But I got a big brain, so I know 2, 2 is the solution. Okay. But yes, you should go through the process checking the work. But again, for sake of time and not making you want to watch a 50-minute, 30-minute, whatever, however long it ends up being video, I'm just going to tell you that the solution is 2, 2. Okay, because again, that's where it crosses. So on this one, we're going to graph them, but then what we're additionally going to do is we're going to identify how many solutions it has. So 2x minus 2, and then I have negative 2x plus y equals 4. For this one, I'm going to switch it up. I'm going to actually, to get the second equation, I'm just going to add 2x over. I'm going to actually graph this one in slope-intercept form. So then I'm going to have y is equal to 2x plus 4 for my second equation. Okay, instead of finding the intercept, because again, I know that's what most of you are going to do, and so might as well just do it in a form that you're comfortable with. So also you should be aware that there's always going to be different multiple possible ways to solve a problem, so it kind of exposes you a little bit to that. So let's go ahead and graph the first equation, which is 2x minus 2. So I'm going to put a dot at negative 2. Slope is 2 over 1, which is, I think this is the same one. Yep, same equation we had last time. So up 2 over 1, up 2 over 1. There we go. Make a line. Oh my gosh, rectangle again. Yeah, there we go. So there's my line. And then the other equation is 2x plus 4. So let's try that one out. So I'm going to start at 4, and this time I'm going up 2 over 1. Not enough room to keep going. So I'm just going to go down 2 and down 2. And then again, connecting the dots. I do have the line tool this time, thank God. All right, now notice that they do not cross. Well, visually, I can tell that this has no solution because they do not cross. But notice that when I rearranged it, I got 2x minus 2 and 2x plus 4. That means it's going to have no solution. If you look back up here to our table, if they have the same slope, but different y-intercepts, it's going to result in a no solution. So even just, I could have even gone without graphing it and known that it was going to have no solution to the system just by looking at the equations. But graphing it does give us a visual, so it's useful. So let's go ahead and type our solution. There is no solution. Pretty easy, right? I gotta remember I'm using the rectangle tool, so I'll have to get rid of it for the next one. All right, and now for the next equation, same thing. I'm going to go ahead and put it in slope-intercept form because, again, all I need to do is add that 3x over. So let's go ahead and do that. And then my equation is y equals 3x, and I believe that's minus 3. Ooh. 3x minus 3. Okay, and so again, looking at the equations, let's preview this a little bit. Notice how I have 3x here and 3x here. They have the same slope, but they have different y-intercepts. This tells me right off the bat that it's going to end up in as no solution. But we're going to draw it because why not? It gives us a visual just to kind of confirm that it is going to be no solution. So I'm graphing 3x. I'm going to start at 0 because that's the y-intercept, and then going up 3 over 1, down 3 over 1. Draw my line to connect those bad boys. All right, and then last equation is 3x minus 3. So starting at negative 3, and again going up 3 over 1, 3 over 1. Notice how close they are to each other, but they're actually never going to cross because they're just going to keep running parallel to each other. So that's why this one, even though it looks like at some point they might be end up coming close, if you look really closely, they actually are never going to cross. They're just going to consistently run parallel to each other. Okay. So again, this one's going to have no solution. Solution, right? Oh my gosh, the struggle is real. All right, last little bit. Old Lines Bowling charges $2.75 per game plus $3 for shoe rental. Jade's Bowling charges $2.25 per game and $3.50 for shoe rental. How many shoes will the cost to bowl be approximately the same at both places, and what is the cost? So I need to come up with an equation for both graphs. I'm sorry, for both situations. And then I need to graph to find the solution. So let's start with old lines bowling. So, oops, don't want a rectangle. Those dang rectangles keep coming back to haunt me. All right, so looking at old lines bowling, let's go ahead and highlight the important information. We'll do it in green, why not? Old lines charges $275 plus $3 for shoe rental. And then we got Jade's Bowling. Look at Jade owning a bowling. I mean, that's why you aren't coming to class. Jade's Bowling charges $225 per game plus $350. Okay. So let's go ahead and make an equation for old lines. Old lines equation. So we know that it's $275 per game. So we're going to say y equals $275 per game. So 2.75x because it's a repeated one. And then plus $3 for the shoe rental. And then Jade's Bowling is going to be $225 plus $350 for the shoe rental. And the reason why the shoe rental doesn't repeat is because once you rent the shoes, you have them for the game. You don't need to rent them every time you play. Okay. So it's just a one-time charge. Okay. So I got 275 plus 3, and sorry, 275x plus 3 and 225x plus 350. And right off the bat, if I look, they have different slopes. That means that it's not going to be infinite solutions, and it's not going to be no solutions. It's going to have at least one solution because the equations do have different slopes. So let's go ahead and draw. I'm going to start by graphing my y-intercept at 3 for old lines. And then I'm going up 275 over 1. Well, 3 plus 275 is 575, which is about right there. And 3 subtract 275 is about 25 cents, which is right there. Very oddly looking. I'm going to go ahead and draw my line using green. And then Jade's Bowling starts at 225, which is about right there. And she's going up 350. She actually ends up being right there too, which is very useful for us because if not, it would kind of be booty cheeks to figure this one out. 1, 2, 350 right there. All right. And then connect them with the line. There we go. So when I look at this, the solution happens to be this point right here, which is 1. And I believe, I'm trying to guess what that is. 275, what did we say it was? 275 and 575. So they'll be the same at the point 175. So we're just going to go ahead and write that. Oops. This is where I get confunked. So they'll be the same at 575. And what that translates to is that after one game, they will both cost 575. That is literally what that point means. So at one game, they're going to both cost 575. But once we get to 2 games, Jade's going to start being more expensive than Old Lines Bowling. So you should probably support Old Lines Bowling and not Jade's Bowling. Alrighty, and that is how we find the solution by graphing.